Okay, so this is the acid and base practice sack that I've given you, another one that I've given you. So it's a 2019 TSSM key topic test. Now the first question is asking us how many moles of hydroxide we have in 2.5 mole of calcium hydroxide. So you can see here calcium hydroxide has two equivalents of hydroxide in it. So if you're going to work out the number of moles of hydroxide, it's going to be 2 times as much as the number of moles of calcium hydroxide. Pretty straightforward. Just make sure you're counting how many equivalents of hydroxide you see within that species. So you can get the same thing with diprotic bases. If you see diprotic acid, if you see an acid that has 2 protons, then you have 2 equivalents of acid, 2 equivalents of protons, or 2 equivalents of hydronium ions in it. So that's B. Question 2, pH of a 0.1 molar solution of acid. So here, you know, the concentration of hydronium ions is going to be equal to the concentration of hydrochloric acid because it's a strong acid here. And to calculate pH, you use this equation here, which is just that. So that would be pH of 1, exactly 1. You can plug it into your calculator to check. The pH of a 0.1 molar solution of sulfuric acid. Okay, now sulfuric acid, this here is a diprotic acid. Okay, so it has 2 protons to give. The first proton is given away completely. So sulfuric acid's first proton, this is a strong acid, okay? And it'll give away its proton and it'll become HSO4 minus, hydrogen bisulfate. Hydrogen bisulfate, or just bisulfate. And this is a weak acid. So a couple of things we can figure out. If the first proton is given completely, the pH would be 1 if only 1 proton was given. But since we know another proton will probably be given by at least some of the product conjugate base, which is also an acid, it's an amphiprotic substance. So this can act as a base, but it won't. And also act as an acid. So it will act as an acid. It should decrease the pH even more because you're going to have more hydronium ions released by this bisulfate ion, yeah? So the pH should be less than 1. That's the sort of reasoning is the pH would be 1 if you lose only 1 proton from sulfuric acid, but you'll probably lose some more from the product of sulfuric acid acting as an acid, so you should get an even more acidic solution. So because we worked out up here that a 0.1 molar solution of a strong acid gives us a pH of 1. So this is one of those nice questions where like it follows on from a previous question. The pH of a 0.1 molar solution of calcium hydroxide. Okay. So calcium hydroxide we know is a base. So the pH is going to be definitely greater than 7. So that eliminates a couple of answers. This is one of the questions where I'd go by like some kind of elimination route just to like figure out the answer a bit more quickly. Greater than 1 but less than 7, probably not as well because it's a base. So that leaves us with D. Easy enough. Question 5, which of the following is not correct about water at a pH of 7 at 25 degrees Celsius? Okay, 25 degrees Celsius, I'm immediately thinking the ionization constant, which is 10 power negative 14 m squared. So that's the concentration of hydronium ions multiplied by concentration of hydroxide ions gives us that. So it is able to self-ionize, that's correct. So we're looking for the not correct answer. The addition of NaCl will have no effect on the pH. I'm pretty sure salts don't have any effect on pH. So that's correct. There are H3O plus ions present in the sample. That is correct. And adding an acid would increase the pH is incorrect. If you add an acid, the pH would decrease, yeah? Acids tend towards the lower end of the scale of pH. Regarding hydroxide and ammonia, ammonia you should know is a weak base. Hydroxide is your prototypical strong base. And we just, I guess, eliminate answers, pick the right one. So not A and B because they're talking about OH and ammonia as acids. So it must be C or D. Must be C because D talks about both being strong bases. The conjugate acid of ammonia, so when ammonia acts as a base and you get an acid, this is your conjugate acid. Okay, so ammonium, this is the ammonium ion. This can act as an acid. Act as an acid to go back. The concentration of H plus is, okay, so this is a key piece of information. pH is 5. So if you're going to work out concentration of H plus, which is also H3O plus, same thing, you use the formula 10 power negative pH, which is basically the reverse of this equation here. So pH 10 negative 5, I guess 1 times 10 to negative 5 molar, which would be 0.00001 molar. 4 zeros. Okay. Concentration of OH minus is, and this is for the same question. So if we want to work out the concentration of hydroxide, we use this equation here, the self-ionization constant equation. So concentration of hydroxide is 10 power negative 14 divided by concentration of that hydronium ions. So that's 10 negative 5. That would be 10 negative 9 molar. So 1 times 10 to the negative 9 molar. A. Okay, so question 10. What concentration of a diprotic acid would be required to make up the solution, assuming both protons go to 100% dissociation? Okay, so diprotic acid, so that means H2X, okay, and both of these are strong protons, which I don't know if strong protons is a thing, but both protons will be given away completely. So we want to make a pH solution of 5 from this. So this here, just looking at it straight away, is a hard question, but we can work it out from backwards. So if this is the concentration of hydronium ions that we need to get a pH 5 solution, okay, 1 times 10 to the negative 5 molar, and we have a diprotic acid that is strong. The diprotic acid, which has 2 equivalents of protons each, yeah, you would have to have half as much of that in order to get as much hydronium as you need. So basically, because we know that this acid will give off 2 protons each, that means overall we would have half as much acid required to get that amount of hydronium. That's the logic behind this. So I just multiplied the concentration of the hydronium ions by half, and that should give you 0.5 times 10 to the negative 5 molar, or, and I guess they have a lot of dots, so that will be 0.000005 molar. So just moving that decimal place across 5 times gives us this one, 5 zeros. Yep.
So if it's H1X, would you do a third of the H3O?
So if it was just a single strong acid, same concentration, because you would need to have the same amount of acid as hydronium. If you know, because the acid only releases 1 proton, and if you want to get 0.00001 molar of hydronium ions, you need the same amount of acid, because the acid can only release 1 proton at a time. So the question was whether, if it was a monoprotic acid, what the ratio would be between the acid and the hydronium ions, and whether it be 1/3 times the number. I'll write that down. So it wouldn't be this. This wouldn't make sense, because what it's saying is that if you had a monoprotic acid, just some monoprotic acid, you're only getting 1/3 of the number of equivalents of hydronium ions. So that's saying only 33%, like 1/3 of that acid is releasing the protons. So that wouldn't even be a strong acid. What you would get instead is like this one here, this triprotic acid. Hang on. Am I doing this the right way? Yeah. Yeah, I think how I explain it makes sense. So if you want to just listen it over, it'll be all recorded here. Yeah, so just my logic up here is that if you have a diprotic strong acid, you know that's going to release 2 protons each, so it's going to produce 2 equivalents of hydronium ions.
I was just confused most of like the labeling, because you have H3O and then you have H2X.
Okay, I gotcha. So H2X, X is just like whatever ion makes up the acid. You know, it could be X could be SO4 2-, it could be carbonate. But it's probably none of those because they don't none of those release both protons as diprotic acids. So they're not like strong for their second proton release. In fact, I don't think there are any acids which are strong for both protons. But yeah, I just wrote H2X, just like that. Just to rewrite this, see if it makes sense to you. Whoops, don't go there. There. So like I said, this is a tricky question, just to talk about. But this would be the ratio here. So ratio between the diprotic acid, which produces those protons, or releases those protons, donates them, and the hydronium ions themselves, it's actually 1:2, because for each mole of the acid, the diprotic acid, H2X, 2 moles of hydronium ions are produced. Hence the ratio. Yes, that's correct. That's what I've been saying the whole time. So that's multi-choice. Of course, there'll be a tricky question in multi-choice somewhere. On to short answer. So write full balanced equation, including states for each of the reactions below. So HCl and water. So let's go HCl plus H2O makes H3O plus Cl minus, I suppose. You can combine H3O plus and Cl minus together. I don't know if that really makes sense or is necessary, so I'll just leave it like this. Okay. Nitric acid. It's probably worth noting here, just from the questions that are being asked, that you do need to know like the chemical formulas for these typical strong acids, HCl and HNO3, and before up in the multi-choice, ammonia, NH3, all of those you should know, okay? So not a fan of memorizing things, but I think definitely here it's worth committing these to memory. So here we produce, this is your typical acid-base reaction producing a salt. The salt here is potassium nitrate and water. Okay, so the proton in HNO3 and the OH from KOH, they combine to make H2O. And then the salts kind of just stay aqueous, so they're spectators really. Okay, H2SO4, diprotic acid, and sodium hydroxide, a base that can only receive 1 proton, so you can straight away like predict that you'll need 2 of them. And don't do that. Na2SO4 plus H2O. So it's again acid and a base produces a salt and water, and it all checks out. 2 protons, so 2 equivalents of sodium hydroxide required. Ammonia and water. So that's NH4 plus OH minus. So ammonia strips water of one of its protons, acting as a base. It's only a weak base though. Outline the intermediate reactions using successive ionization equations. So we have to show different ionization equations. An overall reaction of phosphoric acid acting as a polyprotic acid in water. So phosphoric acid, again, another base acid, that you should memorize, H3PO4. So it's just phosphate with 3 protons. So it's a triprotic acid, so you should have 3 ionization equations, okay? Three ionization equations, each one showing the loss of another proton, donation another proton. So the first one with water is where you get this, lose 1 proton, make 1 hydronium, probably show all the states as usual. So it's a 4-mark question, so they're expecting 4 separate equations, I think. And then this product here is amphiprotic, so while it's a conjugate base and can act as a base and go back to phosphoric acid, they want to show successive ionizations, which is successive loss of or donation of protons, yeah? So we're going to take that and make that go through another acid reaction, so act as an acid, and so that becomes HPO4 2-, hydrogen phosphate. So it was dihydrogen phosphate, now it's hydrogen phosphate, produces another hydronium ion in that reaction, and then it goes through another cycle as an acid to finally become something that is no longer amphiprotic. It can no longer act as an acid. And if you want to put that all together, I mean, ultimately what you would do is you would eliminate all of those intermediates. So wherever there's, so I'm just going to cross out like all the intermediates, although you shouldn't. You should just leave it as is. Like if you were to combine all the reactants together on one side and all the products together on the other side, like because these are on the same side, they would like eliminate each other, right? So the overall reaction is going to be, you add all the waters together, you get 3 waters, and you're left with this phosphate ion, and you get 3 hydroniums because you've added them all together. So you see here you've added this and this and this together to get that, 3 of them, and then you've added this and this and this to get 3 of them. Okay, and you've eliminated all the intermediates, because yeah, if you combine all of the reactant sides together, I'm not going to write out the whole thing, but you would have like phosphate plus dihydrogen phosphate plus hydrogen phosphate plus all those waters makes dihydrogen phosphate plus hydrogen phosphate plus phosphate plus all those hydronium ions. And then like if you have a product on the reactant side, you can cross them out because it's as if like they weren't needed in the equation at all, if that makes sense. Now you wouldn't actually cross those out on the test, just leave them there, because we're trying to show those 3 intermediate reactions, and then this is the full reaction here. Rightio. Classify each of the following by placing a tick in the appropriate box. HCO3-, and that's amphiprotic because it can gain a proton or it could give away a proton, so it's an acid and a base, so therefore it's amphiprotic. Carbonic acid can't really gain a proton, so it's only really an acid. CO3 2-, that is a base, can't give any protons, so it's not an acid. Acetic acid here, so this here you should also know is acetic or ethanoic acid. This is a standard weak acid, find it in vinegar. And this here is ethanol here. Technically, ethanol is a super weak acid, but I think we'll consider it neither an acid nor a base. I don't think we talk about alcohols at this level as being acids at all. Okay, so 5 marks if you get, you only get 5 marks, I guess, if you get all the rows correct. Calculate the pH of a solution formed when 1.2 grams of HCl is added to 800 mils of water. So this is a calculation question, a few steps. So we need to convert the mass of HCl into number of moles of HCl, and then turn that into concentration of HCl and therefore concentration of hydronium ions, and then that we can use to produce pH, get the pH. So mass of HCl is 1.2 grams. Number of mole of HCl is going to be mass of HCl divided by molar mass of HCl. So that's 1.2 divided by 1 plus 35.5. Get my calculator out here. So 1.2 divided by 36.5. So hang on, just make sure you can. So 0.033. I'll just type it in. Well, that's, yep. Yeah, 1 plus 35.5 is 36.5. And so that's the number of moles of, sorry, that would be the moles there. Now we can work out the concentration of HCl now is 0.33 mole divided by 0.8 liters. That will give us our molarity. So really we should, hang on, I'll collect this number. Can I do this? No. Ants divided by 0.8. That will give us our concentration 0.041 molar. Sorry that the formatting on screen is not awesome. .41 molar, and that's going to be the concentration of hydronium ions because it's a strong acid, so the equivalent of the strong acid with hydronium ions is the same. And so pH finally is negative log 10 of the hydronium ion concentration. So I can do that too. Negative log 10. I'm just going to go negative log of answer, because I'm pretty sure it defaults to log base 10, so it's pH of 1.4. And you can confirm that with your calculators. So that's 4 marks there, I guess. 1 mark for working out molar mass, 1 mark for calculating number of moles, 1 mark for equivalent, equating the concentration of hydronium ions with HCl, and then pH calculation for 4th. Okay, dilution question. 400 mils of solution of pH 3 is diluted to 800 mils. What is the new pH? So I would work out the concentration of hydronium ions, which is using 10 power negative pH. So 10 power negative 3, 1 times 10 to negative 3 molar. Now when that is, so we use C1, so the full way is to use C1 V1 equals C2 V2 to work out the effect of your dilution. C1 is this. V1 is 400 mil, or 0.4 liters. Let's just use liters. It doesn't matter if you use mils or liters really in this equation, as long as you use the same units for V1 and V2. So V1 is in liters, V2 is also in liters, and C2 is what we want to find. So this is H3O plus diluted. So just plugging in all these values, 1 times 10 to negative 3 times by 0.4 equals concentration of H3O plus diluted times 0.8. I'm going to do a little rearranging. 1 times 10 to negative 3 times 0.4 divided by 0.8. That should give you your concentration of H3O plus, and then you've got to work out the pH from there. Oops, go down. Times 0.4 divided by 0.8. Okay, so that's 5 times 10 to negative 4. So pH is going to be equal to negative log 10 of that. 5 times negative 10 to negative 4. Okay. Which is 3.3. Okay, pretty standard. Calculate the pH of a 0.1 molar magnesium hydroxide solution. So first thing you note, this here is 2 equivalents of hydroxide. So the concentration of hydroxide is going to be 2 times the concentration of magnesium hydroxide, which means you have 0.2 molar of hydroxide. Now to work out pH, you need to have concentration of hydronium ions. So we use this equation here, the ionization constant of water. Oops, I'm starting to overlap a little bit. To work out the concentration of hydronium ions. So concentration of hydronium ion equals 10 power negative 14 divided by concentration of hydroxide, which is 0.2 molar. So I don't know, is that going to be 5 times 10 to negative 13 molar? So pH, negative log 10 of the concentration of hydronium ions, which is 5 times 10 to negative 13. And that should give you your pH. And just to make sure your number is bigger than 7 because you're dealing with the base. So 12.3. Did I type that in? Yep, 12.3. Yep. So the reason why I multiplied the concentration of when I figure out the concentration of hydroxide ions is 2 times concentration of magnesium hydroxide, is because you have 2 equivalents of hydroxide in 1 magnesium hydroxide, yeah? Can you see here that there's 2 hydroxides there? So 2 equivalents, yeah? Which means each magnesium hydroxide will give you 2 hydroxide ions. Hence why the concentration of hydroxide ions is 2 times that. Okay. Let's not skip this question. So 2 grams of HCl and NaH are added to 2 liters of pure water. Calculate the pH of the solution. Let's do it. So 2 grams of HCl and NaH. This is going to be a reaction where, this is a hard question too, where you don't get complete neutralization of one of the species. So whichever one of these is going to, I'll just do it in whole. So just writing out the equation. If you had equal amounts of moles of HCl and NaH, you would have a neutral product solution. So you have a solution where there is no excess protons, or no excess hydronium ions, and no excess hydroxide. But if you have 2 grams of each of them, there's a chance that it's not going to be exactly the same number of moles. Okay, so you're going to have an excess of one of them. So number of moles of HCl is going to be mass of HCl divided by molar mass of HCl. So that's 2 divided by 1 plus 35.5 or 36.5, yep. I'll leave that, I'll calculate in a sec. And then we've got number of moles of NaH is going to be mass of NaH divided by molar mass of NaH. So that's going to be 2 grams divided by 1 plus 23 plus 16 or 40. And I'm going to calculate these now. Just looking at it quickly, HCl is going to be in excess because it has a smaller molar mass, so you have more moles of it. So 0.0273. So you have that. Oops. Accidentally clicked my keyboard. And then 2 divided by 40, so 0.05. Did I do that correct? 2 Oh, sorry. This was meant to be 2 divided by. Thank you. So that's 0.055. and this one here is 0.05 mole. So you have more HCl than NaOH. I'm not gonna lie, this is actually like a year 12 kind of question, because what it gets you to do is work out how much excess you have of one substance. So you have an excess of HCl, and then you have, the next question is how much excess? And so the excess of HCl, yes, just thinking about it logically, it's like the amount that you have is the amount that you have left, the excess amount you have, is the initial amount minus the amount that's been reacted. So if you know that HCl reacts like in a 1-to-1 ratio with NaOH, okay, if there's 0.05 moles of NaOH, that's the amount of HCl that reacts with the NaOH, okay? So it's going to be really 0.0055, which is the total amount of HCl, minus 0.05 moles, which is the amount of HCl that has reacted with the sodium hydroxide, which leaves us with 0.005 mole. I would use the exact value on your calculator to be sure. So that's the mole of HCl we have left over in the reaction, okay? And so finally we need to work out the concentration of HCl. You can work out the number of moles of hydronium first, whichever you like. I'm just going to work out concentration of HCl first, which is N over V. So this is using the equation N equals CV, just rearranging it for C. 0.005 divided by 2, that's the volume. And that gives us 2.5 times 10 to the negative 3 molar. And that's the concentration of hydronium ions. And finally, we're left with pH, negative log 10 of H3O plus equals, yeah. So let's just, I'm going to plug all those through on the calculator. So basically, take this minus, yeah, that's not my answer. I want this one. So how do I get this one down? Does it come down? And that's, and divide that by 2. And then negative log 10 of that. Gives me a pH of 2.6. Now, you probably note that like throughout this entire test, I haven't really talked about significant figures. I continue to put that off. But technically this question only has one significant figure because we use this 2 liters here in the calculation. So if you're going to be very precise, that is the answer, pH 3. Anyway, that's a discussion for another day, significant figures. Okay, we've got 10 minutes left to do 2 questions, 7 marks. Give an explanation as to why ethane does not donate a hydrogen atom and act as an acid, whilst ethanoic acid does. Ethane. So back to organic chem. Ethane is your hydrocarbon here. None of these protons here are acidic. That is like they're readily given away. Okay? So these carbon-hydrogen bonds on hydrocarbons are pretty strong in terms of reactivity with water and stuff. But ethanoic acid, if you compare that, that's not ethane. I just drew something else. Ethanoic acid looks like this, and we should know that this here, this proton here is an acidic proton. So if you're going to answer this question, I would go from the route that talks about their structures and talks about the strength of these carbon-hydrogen bonds, okay, and the fact that these result in protons that aren't readily donated. and compare that with ethanoic acid's protons here. Well, single proton here, which is acidic because it can easily be lost, and then the ion, the charge that is left behind on this structure is something that can be managed. So this charge here that's left behind is something that can be managed. So whenever you have an ionization reaction with donation of a proton, you're left with a cation and an anion. The anion has to be something that's stable. Okay, so I'm not going to write the full explanation for that. If you want to have a look at that, the answers I'm sure there are examples of good answers in the solutions. And finally, the last one, explain why a weak acid can have a lower pH than a strong acid. So strong acids, we know, give 100% of their protons, whereas weak acids, less than 100% ionization. So only less than 100% will give away their protons. But we also talked about the difference between concentrated, we talked about like strength, strong / weak, as being one like form of descriptive for acids, but we also talked about concentration as like another descriptive, okay? So strong versus concentrated. So you could have a weak, very concentrated acid, and that could have a lower pH, that is, be more acidic than a strong but very dilute acid, okay? So in the case of like a strong, relatively dilute, the pH of this could actually be higher, than a weak concentrated acid. With a weak concentrated acid, you could have significant amounts of protons in solution, so therefore have a lower pH. And as a result, yeah, this here is where you can have a lower pH acid compared to a strong acid. So you just turn all of this into wordy words and it'll be good. Okay, so that's the run through. Hopefully that helps there.